Say we know that the temperature in Sacramento from midnight t equals 0 to t equals 24, midnight the next day, t equals 24, is modeled by this function right here. Okay, apparently it's in Fahrenheit, or at least that's implicit. Approximate the average temperature in Sacramento over the course of a day. Okay, here's what I want us to do to kind of get an intuition for how we can do this. In a similar fashion to what we've been doing, well, first of all, I'm going to graph this. So we're concerned about from t equals 0 to t equals 24. This function is going to look something like this. It looks like it increases. We know how a sine wave goes. And we know that when we plug 24 in right here, the 24s will cancel and we'll have sine of pi, which is 0. So it should land back at 60. So here's what our curve looks like, something like this. If I wanted to find an average, what you would do, well, first of all, immediately this is a problem because f changes continuously. F is always changing. The temperature is continuously changing. And in order to find the average, at least up until this point, in order to find the average of something, it's a finite set. But f of t is going to output infinitely many values from t equals 0 to t equals 4. So how do we find an average of an infinite set? Well, kind of in the spirit of what we've been doing recently, what we're going to do is grab maybe, I don't know, like 4 test values. Something like this. And then just average those, right? So we'll start with n equals 4. And then maybe I'll call this f of t1, f of t2, f of t3, and f of t4. All right. So if I wanted to find the average of those, what I could do is simply add those up, f of t1 plus f of t2 plus f of t3 plus f of t4. And of course, you would then divide by how many points there are. It's typical average store. You would go, hey, what's the average of these values? I would divide this by 4, and that would be the average of those 4 sample points. But of course, we want to be much more accurate. So what if we were to take, instead of just 4, what if we were to take n? So I'll draw the same curve again. So let's imagine we grab n of these sample values. So this continues, ... Here's the first one. That would be f of t1, f of t2, f of t3, and maybe continues to f of t sub n minus, I guess that would be n minus 2. This one would be f of t sub n minus 1. And then last but not least, we got f of t sub n. All right? So if we were to take the average of those, I would simply sum these guys. F of t1 plus f of t2 plus f of t3 plus ... plus f of tn. And of course, in this case, I'll divide this by n, all right? Okay, but here's the idea. What I could also do is, in the similar way with the integrals, splice this interval into n equal pieces, and that would be 24 minus 0 all divided by n, and that will count as my delta sub x, right? But wait a second. Doesn't that imply that 1 over n is also known as delta sub x divided by my 24 minus 0? So what I can do is go to this obvious average. So this is kind of like my average value for f. And it's going to approximately equal this, assuming this is a huge sample size. But using this idea, I can replace this 1 over n, so I'll rewrite this, f of t sub 1, yada yada, f of t sub 2, plus dot dot dot, plus f of t sub n. And this is the same thing as, look, 1 over n is the same thing as delta x over 24 minus 0. So that would be delta x divided by 24 minus 0, minus 0, of f of t sub 1 plus f of t sub 2 plus dot dot dot, of course, f of t sub n. But wait a second. That's the same thing. If I distribute this delta x, I'll have 1 over 24 minus 0 times the sum. I'll cut to the chase here. The sum, as k ranges from 1 to n, here's our k values, 1, 2, yada yada, all the way to n, of f of, excuse me, wrong f, capital F, f of t sub 1 times delta sub k, or excuse me, not t sub 1, t sub k, delta sub k of x. Okay? Now, I think that looks a lot like an integral. Indeed, if we wanted our average to be a lot more accurate, we would simply let this n approach infinity. That implies that the exact average, and this is a definition that we have here, the average value of f is actually, by definition, in this case, 1 over 24 minus 0, if you so choose, times the integral from 0 to 24 of f of x, or I'll use t dt. This is a definition. Let me define it for an arbitrary function. We're going to come back and approximate the temperature in Sacramento in a second, but huge definition that I need us all to know. The definition. The average value of a function, integrable function, f over a to b is, by definition, you would go like AV of f, and that is equal to 1 over b minus a times the integral from a to b of f of x dx. All right? So that's something we got to know. Average value of a function. Especially when we start talking about this new mean value theorem for integrals, we need to know the average value of a function in order to comprehend that. Okay, but now let's use this new sort of motivated definition to actually approximate the average value of f. I'm not going to use a ton of rectangles because this function is not super pretty if t isn't very well behaved. So how about I do this? Let's sample at t equals 4 hours. Let's do t equals 8 hours. T equals 12 hours. T equals 16 hours. And last but not least, let's do t equals 20 hours. So our average value, we just need to approximate it. The average value of f is equal to 1 over 24 times the integral from 0 to 24 of f of t dt. But that is approximately equal to 1 over 24 times the sum of f of, so I'll label these 1, 2, 3, 4, and 5. This is a huge approximation. F of, let's go t sub 1 plus f of t sub 2 plus f of t sub t sub 3 plus f of t sub 4 plus f of t sub 5. And of course, I do have to think about we can imagine these as right endpoint rules. Oops, I have forgotten my, the base of my rectangles. So let's see, are they all 4 hours? Oh, it is all 4 hours. Okay, so times 4 hours. So that would be 1 over 6 times the sum of these. F of t sub 1, let's see what happens. I grab t sub 1, 4, plug it in right here. That's going to give me pi over 6. That's 1/2. 30 times 1/2, that would be 15. 60 plus 15, 75. Plus f of t sub 2. I shouldn't have done so many rectangles. This is going to take forever. That's pi thirds. Sine of pi thirds is root 3 over 2. Root 3 over 2, 15 root 3, 60 plus 15 root 3. For f of t sub 2. F of t sub 3. Okay, so t sub 3 is 12 hours. That's sine of pi halves. That's 1. So this is going to be hot. This is hot part of the day. That's 90 plus f of t sub 4, 16. That's 2/3. Of course, that's going to be the same as this right here. So I'll just do, well, no, I'll show it out. 60 plus 15 root 3. And f of t sub 5, I'll bet, is 75 again. Yep. So we got 20 hours. That's 5 pi 6. Sine of 5 pi 6 is 1/2. Yep, 75. All right, simplifying this guy. That is, I suppose this would, I really needed the times 4 hours here. This is equal to, okay, so here I've got 150 plus another 150. That's 300 plus 4. So we got 420 plus 30 root 3. All divided by 6. So that would be 70 plus 5 root 3. Root 3 is what, like 1.7? So I'll call that 1.6. This is approximately equal to 5 times 1.6, 78. And that makes sense on a average day in Sacramento. It's probably like springtime or something like that. But that's our definition of average value. I wanted to motivate that a little bit. Where does this come from? And we just used it in an application. And yes, that's good to know. Average value right here. Crucial.